All right. All right, now pumps can be set up in a couple different ways. One way is in parallel, which is what we call a duplex pumping station, and the other is in series. So when pumps are in parallel, you have the line coming in branches, and it splits. So the water can go through either pump. So what happens then is the water then comes together after the water goes through the pump and then is sent out in a single line. So what happens when you've got parallel pumps is you get basically you're getting twice the flow and the same pressure as one pump. Okay, so what you're doing with that is you're pushing twice as much water as you would through one pump. Now, I have to kind of say that with quotes, so to speak, because when you start trying to push a huge amount of water through that pipe, you're going to get a lot of head loss, and that affects the flow in some ways that aren't, that'll actually reduce the flow. You won't get quite twice the flow, but the idea here is that you are increasing the flow significantly, but you're getting the same pressure out of both pumps so that you're not really increasing the pressure. That's on page 134 is where I'm at. Okay. Now, pumps in series, what you do is you put two pumps in a row. So the flow comes into the first pump and the pressure increases. And then you increase the pressure a second time with the second pump. So you get the same flow and 2x the pressure of a single pump. Okay. So that's what happens there. So these are the common ways to set these pumps up. All right, so the parallel pumps, again, they're taking one input, usually they're in a wet well. So you've got your wet well here, and then you've got the two pumps, and they'll both feed out, and then generally somehow that gets into one line that then takes the water out. So if your water level's here, and let's say you've surpassed the ability of one pump to pump it out, a switch will come on and turn both pumps on. So what that's going to do is send water down both these pipes, and eventually that'll get you double the flow. Coming out, the pressure stays the same. Okay? All right. Now, when you have pumps in series, that can be a multi-stage pump like you're seeing there. So what you do, you pull water up into that first bowl or volute, whatever you want to call it. That will pressurize the water and send the same amount of water to the second bowl. I can't tell how many we got here. We used to have this in the lab.
Oh, we've got it next door.
Okay, I don't know if there's 3 stages or 2 on this thing, but what that's doing is taking the same flow and sending it to successive impellers, and every time it does, it gets pressurized more and more. So what pumps in series do is they double the pressure. They don't increase the flow, but they double or triple the pressure depending on how many bowls you've got. Okay? So that's another way to set pumps up. Okay. So we good with that?
Yeah.
Okay. So that's on page 134. Okay, 135, what we've got there is another 2 other types of configurations you can have. The general terminology on this is you have the low pressure side of the pump where the water's coming in. That's called the suction side sometimes because you're kind of applying suction to pull the water up, or the inlet side. You then push the water to the other side, which is where after the water's gone through the pump and it's been pressurized. That's the discharge side or the outlet side. Okay? So that's the terminology there. The inlet suction or low pressure side where the water's coming in, and the outlet high pressure side and discharge side where the water goes out. All right. Now there's 2 basic ways to set pumps up. One is what we call static lift. That's when you lift water out of the downstream reservoir, like an irrigation pump. If you ever floated a river around here, you might have seen some pumps up on the bank, and then the pipe sticks down into the river. That's lifting the water out of the river to the pump. Okay, so that's suction. Static lift is called. There's also what's called static head, which is like a submersible pump. That's when the inlet water is above the pump, so gravity actually pushes water into the pump. Okay. So here's static lift. You've got the pump out of the river, pipe sticks into the river, pulls water out of the river to the pump, pump pumps it out. So you have to lift the water out of the river, okay? Static head is shown here. It's like a wet well. We've got a submersible pump in a wet well. So you just have water flowing in through gravity into that tank, and the water level is going to be up here somewhere, and that's going to put pressure and push the water into the pump, okay? So that's a submersible pump. So we're doing all right with that? So there's static lift, lifting the water out of the river. There's static head, okay? That's a submersible pump there, a pretty big one, I think. So submersible pumps need seals and all that, of course, to keep the water away from the electric motor. Okay. All right. Okay, so that's the basic configurations that you can put these pumps in. All right. All right, now I'm going to jump around here a little bit, but on page 136, we've got that static lift condition. So what you have then is what we call the total static head. Now the word static means not flowing, so that's just elevation difference. So static head is just an elevation difference between 2 points. So you can talk about the static suction lift, because you're lifting the water out of the inlet reservoir to the pump in this case. And then the static discharge head, because you're pushing the water out of the pump. Okay? So that's on page 156. I'm sorry, 136. Yeah, 136. Now, we got a limit here because remember, when you're lifting water out of a reservoir, what's happening here is you've got that impeller spinning and you have a vacuum in the pump. That's the assumption, is that you're creating a total lack of pressure in the pump, an absolute pressure of 0. So what's going to happen if you do that is you're going to have the atmospheric pressure pushing on that water. And what that's going to do is it's going to push the water up the pipe into the pump. Okay? Now, if atmospheric pressure is equal to 14.7 psi, how high can you lift the water then?
feet.
34 feet. That's the maximum theoretical possibility for lifting water out of into your pump. We good?
Yeah.
Okay. So you don't have any, you just can't do any more, because what's happening, it's not really pulling the water out of the reservoir. The water's being pushed by atmospheric pressure. That's about 14.7, and you just convert that into feet. That's 34 feet. That's it, okay? So if you're setting up an irrigation pump, you can't put it more than 34 feet above the river, because there's just not enough atmospheric pressure to push it up. Now, in practical terms, it's quite a bit less. I wouldn't try and lift much more than 20, just because you got things like head loss, you got leaks in the pipe, you got stuff like that, okay? So 34 is the kind of the theoretical number, but the practical number is more down around 20 or so, maybe 25. I'm not quite sure, but don't push it.
Especially coming from a river, you've probably got some sort of screen or something.
Yeah, right. Yeah, you just got all sorts of stuff going on there. And what happens if you start trying to lift water too high is you drop the pressure really low in the volute, and the water starts to vaporize in the volute, and then the impeller creates high pressure and crushes those vapor bubbles, and you get something called cavitation. Anyone been around a cavitating pump?
It vibrates like crazy.
Vibrates, and it sounds like it's pumping rocks. That's what it sounds like. It just cracks and snaps, and it can just chew the impeller up. So you don't want to get into that situation. So if you've got a problem with cavitation, you drop the pump down so you're not lifting water so high. You also look at the fittings you got on that intake piping, because more fittings mean more head loss. So try and reduce them, reduce the bends, use a bigger intake pipe. But the first thing I think about doing is trying to drop that pump down, because you can push water forever. You know, we could pump water to the moon if we had to, if we had a big enough pump, but you can't lift it more than 34, okay? But once you get it to the pump, you can just keep pushing it. Just use a bigger pump and just keep pushing it, okay? All right? So that's something to realize there, okay? Okay, now the terminology for, there we go, okay. So this is just showing kind of what's happening in a lift situation. What that impeller does, it spins, it throws everything out, it creates a vacuum, and that's what creates that vacuum that allows the water to go into the pump. So theoretical maximum 34 feet, practical maximum 20 to 25, okay? Now from a pumping point of view, a preferable way to do this is to have static head, to have the inlet reservoir above your pump. That way gravity will push the water into your pump. You don't have to worry about this, okay? That's
keep the pump primed.
Yes, yeah, right. It takes care of a lot of problems, at least hydraulically. Now, what's the problem you got when you have a pump below the intake reservoir?
You have to make sure you valve it up, have a valve in between it so you can
Yeah.
do repairs on the pump.
Yeah, okay,
Or
now,
fluid here.
yeah, right. Yeah, there's two different ways. Well, there's a few different ways to handle this. One is to actually have a pipe that goes from the inlet reservoir down to the pump. Now, that way you got to have it valved off so you can shut it down and pull the pump and work on it if you need to. But a more common way is to use a submersible pump, one of those, okay? So if you're going to use something like that, you got a little bit of a problem getting that in and out of the reservoir and all that. You know, when you look at wet wells, they often have a set of tracks that go down the wall of the wet well, and then they have rollers on the pump and a little kind of a hinge kind of thing where it'll seat in to the pipe so you can just pull the pump up. But the maintenance becomes a problem when you've got a submersible, okay? So,
You've got all those seals and
yeah, you got seals and all that stuff too.
seal alarms. And,
Yeah. So, you know, there's no perfect answer, but those are the trade-offs, okay?
What's a berm?
I'm sorry?
What's a berm?
A berm?
Yeah.
Just some dirt, like a long, thin hill, you know?
Okay.
Just I think they're doing that just to isolate that pump, create like a dry area where it's at. I don't know why they show a berm there. I'm not quite sure. That's kind of weird. Yeah, I don't know what's up with that. Hang on now. I don't know why they got a berm, but they're pointing at a flat.
yeah.
I'm not quite sure what
They
they
didn't know
mean.
how to spell curb.
Say what now?
Maybe they didn't know how to spell curb.
Maybe not. I don't know. That's a good question. So I guess
You got the
my
road right there and a manhole.
yeah, I know. My second answer is I don't quite know what they mean by a berm there. Okay. I don't know.
Concrete section there.
I don't know. Yeah, I'm not quite sure what's going on with that. All right, so now when you've got a situation like that, you have static head, which is just the elevation difference between the reservoir and your pump, and then you got static discharge head. So suction head on the intake side, discharge head on the outtake side. What the total static head then, the TSH, total static head, what that is the static discharge head minus the static suction head, okay? Basically, you've already got some help getting the water into your pump. all that pump's doing is pushing the water from here, because if there were no pump, that water on the intake reservoir would just flow to that level, right? So the pump's just doing this in that case. That's all it's doing, it's pumping that extra little bit. Okay. So we doing all right with that? Okay, we're good? All right, let's just look at some numbers here. So on page 137, how high are you lifting the water into the intake reservoir? Or excuse me, into the pump, from the intake reservoir to the pump, how high are you lifting?
7 feet.
7 feet, yeah. Just subtract the elevations, right? And that's about it. So you're lifting the water 7 feet. How about to the outlet reservoir there from the pump?
20 feet. No, wait, sorry.
Something.
118.
118?
118,
Yeah. So what's the total static head then, as it's called? Well, 619 minus 501, is that 118? So what, 125 total? Add them up. 7 feet from the intake reservoir to the pump, 118 more to get it up to the outlet reservoir. That's one way to do it. The other way to do it is just to take 619 minus 494. And I hope we'll get the same answer. That would be a
Yeah,
good
that's
thing.
what I did.
Okay. Either way. You can either add the two together or just take the final elevation, subtract off the initial. You can do it either way. Same number. Okay. So to get the water up to the pump, you're going 7 feet, and sometimes you got to pay attention to that because you might get cavitation. And then also, when you look at sizing the pump, you're pushing the water 125 feet up. That's what you're doing. Okay. Okay. So we got 7, 118, and a total of 125. How about the other side? What do we got for the static suction head? How much fall do you have on the water going into the pump? 20 feet, yeah. How about how far are you pushing the water up out of the reservoir then? What do we got? So what's the total static head on this then? Yeah, 36. You can calculate it two ways. You can take the discharge head minus the static suction head, or you can take the downstream reservoir, or I don't know if that's called downstream, the discharge reservoir, I guess we call it, minus the inlet reservoir. Either way, that's 36 feet. Okay? That's 36. This is 20. So that's 56. Okay? You good? Because when you're sizing a pump, you're sizing it to push the water up a certain distance. And so that's a big part of sizing a pump, is to know how high you're lifting the water. Okay?
Oh, okay.
Yeah.
So that just made more sense on some of our, the way the plant I'm working at is set up.
Oh, okay. They like that.
They have to our wet well levels by how high it is, but it's actually above sea level or what they were
Right.
doing
Yeah.
to run the flow of the plant. Okay, that actually makes more sense now.
All right. Yeah. I mean, see, surveyors get out there and they reference everything to sea level. That way they can reference everything to everything else they're working on, see?
Well, we had two different guys, surveyors come out, so we have two different places that are actually measured from a different set.
Oh, really? Oh.
Yes, our plant's just on crack.
Okay, all right. Well, hopefully you can get it sorted out.
It's working.
All right.
But just some of the measurements are like off, so
Yeah.
like one wet well that can go up to 105 feet. Another one that, if you get it above 120 inches, your street treatment, you have sewage flowing down
Oh,
the
really?
street.
Okay, all right, so you gotta get that worked out.
They have it worked out. We have our parameters where we have them set up, but
Yeah.
it's just weird the way they did it.
Okay, yeah, all right. Yeah, surveying gets a little complicated sometimes.
Right.
More than it maybe should be, but anyway, sometimes it does.
Well, that, the plant's over 60 years old.
Yeah, okay, that explains a lot of things. All right, now, let's look here. Now, that's a big part of the story is how high you're lifting the water, okay? But the other part is you got to overcome head loss. Okay, so when you turn that pump on, the water starts to flow, you start getting head loss. So not only does the pump have to lift the water, it also has to overcome the head loss. Okay, so when we talk about what we call the dynamic head, which is really what we design a pump on, that's the static lift, but you have to add the head loss or the friction loss to it, okay? And add those two together. And that's what the pump's overcoming to move the water, the lift and the head loss both. Okay, so total dynamic head, as it's called, TDH, is the elevation head plus the friction loss. And this is how we figure out how to size a pump. We look at this number. It's the total energy that the pump has to develop to move the water from one reservoir to another. All right, so let's look at an example here on page 139. Let's say we got 1,300 gallons per minute. We got 8-inch pipes, C100. On the suction side, we got 26 feet of pipe, a standard elbow with an L over D of 64, and an ordinary outlet with an L over D of 20. Now, I'm giving you those L over D values, but you can look them up, right? I just put them on there just so we're not running all over the book looking everywhere, okay? Okay. That's on the intake side. On the discharge side, we got 72 feet of pipe, a standard elbow with an L over D of 64, and an ordinary inlet, L over D of 30. Okay. Let's find the TDH, the total dynamic head for this pump. Let's say we got 1,300 gallons per minute flowing through it. For 8-inch pipe, C100, the head loss is 4.85 feet per 100 feet. That's on page 108 where that chart is. So what I did, so we're not running around too much, I went to page 108 and looked at the head loss for 8-inch pipe, 1,300 gallons per minute. Okay. And that's 4.85. And I went to the other chart on page 123 and looked up the L over D values for the fittings we're using. Right? And I wrote them down. All right, let's figure out how much head loss we got, or what the TDH is for this pump. Okay? So let's just kind of head on through this. What's the total static head for this system? I think this is one we used a little bit earlier, so I think we already have that number, but how high are we lifting the water?
36 feet.
Yeah, so 678 minus 642, is it? Yeah, 642, 36 feet. So we're lifting the water 36 feet. That's called the static head. But we got to figure out what the dynamic head is. We got to figure out what the head loss is going to be to push the water through this pipe. So what's the total length of piping on this thing?
Total is 186.
Yeah, 186, because we got on the suction side, we got 26 feet. On the discharge side, we got 160. So we're going to take 26 feet plus 160, and that's 186 feet of pipe. Okay. But we've also got the fittings. We got 2 standard elbows. Okay. 2 of them, they've got an L over D of 64, and we've got 8-inch pipe, which is 0.667 feet. So I got 2 elbows, L over D is 64, and the diameter is 0.667 feet. So when I multiply that out for 2 elbows, I'm going to get 85.3 feet of pipe. So pushing that water through those fittings will get us the same head loss as pushing the water through 85.3 feet of pipe. Okay. Okay, the ordinary outlet is 20. That's L over D is 20. Multiply that by 0.667 feet. And what do we get? Do we get 13.3? And then the inlet has an L over D of 30 times 0.667 feet. Ought to be pretty close to 20. Okay. So if I add up all those fittings, that's going to be 85.3 for the 2 elbows, 13.3 for the outlet, and 119.18.6. Okay. Yeah, I think that's right. Yeah.
Okay.
So all of those 4 fittings, the 2 elbows, the outlet, and the inlet, have a total equivalent length of 118.6. We okay with that? Okay, the length of the pipe is 186, plus we got 118.6 for the fittings. So the head loss for this is like we're pushing water through 304.6 feet. Okay, that's how we figure out the head loss. We got 186 feet of actual pipe, and the fittings have the same head loss as 118.6 feet of pipe. So when we add those up, we get 304.6. So now I can find the head loss. Because I got 4.85 feet per 100 feet. That's the head loss. And I got what, 3.046 100-foot lengths? When I multiply that out, I get 14.77 feet of head loss. Yeah. This is the length of the pipe.
Oh, is it 304.6? I think it's 0.46.
Oh, here I did it like this, 3.046, because that's 100-foot length. So I think that 304.6 divided by 100. That's where the 3.046 comes from. All right. All right, so when I turn that pump on, it's going to start pushing against that static head of 36, and when that water starts flowing, it's got to develop an extra 14.77 feet, okay, to push against the friction losses. So it's going to have to push against 50.77 feet of resistance is what it's going to have to do, okay.
And again, since it's the total dynamic head, it's still just gonna be in feet and not feet of resistance or anything like that for special?
Feet are feet. The pump doesn't know the difference between lifting water and pushing its head loss. It's just
Gotcha.
resistance is all it is.
Okay, I just wanna make sure,
Yeah.
you said that, feet of resistance, I'm like,
Yeah,
just wanna make sure I get the proper,
yeah, sure. It's the same.
units and stuff.
Pump doesn't know the difference. Yeah.
Copy that.
Okay. Now let's just look at one thing here real quick. Now, when you get a pump, we'll come back to this, but let's just touch on this. When you get a pump, you get what's called a pump curve. Okay.
I remember those.
Now, a pump curve graphically shows what a pump will do. Okay. Now, this is for a pump that I'm on page 147. This is for a pump that is a single stage pump with no controls, no variable frequency drive, no variable speed drive, none of that. Just a pump that you turn on. Pumps, you just turn them on and they go, okay? There's no gas pedal on a pump. It just goes. Unless you've got fancy controls anyway. So this is what we call the TDH line. You'll notice we got TDH and flow on this curve. That's the two things we've got. As you push more flow, the head that the pump develops drops. The power that goes to the pump is split between flow and pressure, head, okay? So if you want more flow, you get less pressure. There's only so much energy in the pump to go around, so much power actually, okay? So that's the basic line of a pump. It's called the head curve. More flow, less head. All right. Now what you want to do is pick a pump pick a pump that fits what you want to do with it. Okay. So what do we want to do with this particular pump? We want 1,300 gallons per minute, and we're going to push it. Was it 50.77 feet? Right. That's what we want to do with this pump. That's what we just calculated. Okay. So if I'm looking at this graph, I'm going to go here, 1,300 gallons per minute, 50.77 feet. I'm nowhere near that head curve, okay? This pump is not built to do the job that we want to do with it. It's overpowered, okay?
Touch.
Yeah, quite a few touches, yeah. Because I'm up looking against that blue line that I drew up here, okay? Here's where the pump wants to run, but we're going to ask it to do a job down here. And it's kind of like, you know, using a professional athlete to play on a 7th grade basketball team. It just isn't quite fit, okay? All right? So that pump is way oversized to do that job. And what it's going to do, it's going to take that point we want to push it. It's going to really kick up the gallons per minute and get more resistance. So it's going to really kick the flow way up, which may not be what we want for this job. The other thing is if you look at those efficiency lines, we're probably not where we want to be with that pump, okay?
Didn't even make it to efficiency lines.
Yeah, I know. Well, what it'll do, it'll run. It won't stay on that point because that isn't on the operating curve, not on the head curve. So it's going to kick out over here. It's going to end up running over here somewhere. At a real high flow. Okay? And a bit more additional head loss because it's pushing more flow through that piping system. So if we're going to run this pump, if we want to pick this pump, we're going to want a point. We want to be running right up in there somewhere. We're going to do our calcs on the system at 1,300 gallons per minute. We're going to be looking for a TDH around 140. That's where that pump wants to. If it's going to pump 1,300 gallons per minute, it wants to be at a TDH of 140 thereabouts. Okay.
Should that be adjusting like the pipe size to make it flow, or the pump?
No, this one, yeah, the pipes are what they are. I mean, you have a system, you pick a pump to match the system. And it's not like bigger is better.
No.
You can get into problems with hydraulics if you oversize your pump dramatically like this is. This is not the pump for this job. It's not what you want. You pick a different pump. And the vendors will give you software where you can plug in your piping system and your elevation change and all that, and it'll select pumps for you that fit it, that do what you want to do. Yeah, okay. All right, so we'll finish this up Friday. We'll also go over the stuff for the test. I'll get you some homework. Well, it'll be, why don't I just give it to you while I'm thinking about it. Let's see. About 14.1, 14.5, and 6. They'll take a little while, but and I'll make these do. Here'll be the deal. So 14.1, 14.5, and 14.6. Now officially these will be due Wednesday, which is the 27th. But I've been teaching here a few years, so I'll take them on Monday too. All right. Sometimes I don't get them on the Wednesday before Thanksgiving, sometimes it doesn't happen, so if you're, I can take a Monday also, but,
Okay,
okay?
okay,
Yeah,
so,
we're gonna go over another example on Friday, I know a lot of you won't be here as long time, so mentioning all this, okay? So on Friday, we're gonna go over the stuff for the test, the topics, and then we'll try and cover one more of these pump calculations too. So this stuff will be due Wednesday, though I will take it the following Monday, okay? Which I think is, I think that's the first, I think. All right.